Welcome to the talk for our paper titled PROPEL, Probabilistic Parametric Regression Loss for Convolutional Neural Networks. In our work, we address the problem of learning the mapping of 2D images of hands onto 3D orientations. These 3D orientations are represented by two orientation angles, which are the azimuth and the elevation rotation angles. One of the major challenges that we face in our dataset is the symmetry problem, whereby due to the absence of depth information, different opposite orientations of the hand may result in similar input features. When we have this kind of ambiguity in the dataset, we notice that using existing regression techniques result in a big bias where the models try to fit into the data and end up having a large error for all the orientations. This motivates the need for a probabilistic regression technique whereby it can address the ambiguity within the dataset by having multiple hypotheses in the target. In the existing literature, probabilistic learning has been addressed using CNNs, where the CNN output a model distribution PM, which is used to learn a ground truth distribution PGT using a specific loss function. In case of classification problems, an input image is often mapped onto a discretized probability distribution function in the output. This distribution function is often learned using a cross-entropy loss. In cases where ambiguity exists within the classification problem, the target distribution is able to handle the ambiguity and show exactly the probability for each class. For regression problems, the target space is often constrained using a heat map distribution where the continuous target space is often converted into a discretized version of the space. This is usually learned using a mean squared error function. Using a CNN to learn a heat map distribution results in models that are more complex, having more parameters as compared to directly learning the target space. The heat map distributions themselves are discretized, so they may introduce errors in the output of the model. Having higher dimensional targets usually means increase in number of model parameters in order to map to higher dimensional target space. With increased model size and complexity, the models are prone to overfitting and usually require sophisticated regularization techniques as well as additional training data. Towards this end, we propose PROPEL, which enables a CNN to directly learn parameters of a mixture of Gaussian probability distribution. PROPEL is fully differentiable and has an analytical closed-form solution to the integrals. It can therefore be applied onto existing CNN as well as using existing optimization techniques. We propose a generalized solution for PROPEL, which has generalized equations for high-dimensional targets as well as generalization for multimodalities by having multiple number of Gaussians in the target distribution. In our experiments, we show that models using PROPEL generalize better while having 10 times less parameters. The loss function we define is using a metric from existing literature, whereby we use a ground truth distribution defined as n-dimensional Gaussian and a model distribution defined as n-dimensional mixture of Gaussian. In our case, the CNN learns directly to predict the parameters of the model distribution, which are the mean and variances shown here. In order to learn these mean and variances, we can take partial derivatives of the loss with respect to each and backpropagate the errors onto the model parameters. We apply PROPEL onto two different problems using a small VGG-like network. We look at hand as well as head orientation problems. For hand orientation estimation, a model trained with PROPEL has 10 times less model parameters while surpassing the state-of-the-art accuracy. For head orientation problem, our model achieves state-of-the-art accuracy while using 50 times less model parameters as compared to the state-of-the-art. In conclusion, we showed the importance of probabilistic regression. We highlighted some of the limitations of existing work that utilized heat map-based CNN regression. We then propose PROPEL that addresses these limitations by having CNN output parameters of a mixture of Gaussian distribution. Using PROPEL, we can train models that are 10 times smaller while having similar or better accuracy as compared to the state-of-the-art. In our future work, we wish to explore looking at higher dimensional targets such as human body pose estimation and hand pose estimation problems. Another direction to look at is to explore different number of Gaussians in the model distribution. And lastly, we wish to explore using covariance terms so that we can model covariant target variables. Thank you for listening, and we hope to see you at our poster session later.